I'm Lilli Thompson, and I'm going to talk to you about cross-platform game programming with PlayN. So first of all, just some background on who I am. My background is actually in the console game programming space. So I worked at a number of big studios like Sega and Sony and Pandemic Studios. And after doing that kind of programming for a while, I joined Google as a software engineer and did sort of web stuff with Google. And then I really missed the games industry after about 2 years of doing that. And so now I joined the Chrome team. So I'm a game developer advocate with the Chrome team, which means that I'm a software engineer who works with developers who are working with game technologies that are priorities for Chrome. So the big three for me, the things I really love to talk about, are HTML5 and WebGL and PlayN, which is what I'm talking about today. And if you want to talk to me about any of these things, I'll be really excited. There are lots of ways to reach me on Twitter and Google+. Are two really good ones. So the structure of what I'm going to talk about today is I'm going to be introducing the PlayN API for developing cross-platform games. And so the first half of the talk will be background information about what PlayN is and what you can do with it and what has been done with it. And then the second half of the talk is sort of more practical engineering-oriented information. So that's like how these APIs actually work, what it would look like to you as a programmer if you wanted to get started doing these things, and all that. All right, so first of all, let's define the problem. What exactly is PlayN? So it's code. At the end of the day, it's an open source Java project. You import this into your Java project, your source code depends on it, and what it does for you is it allows you to compile out versions of your one game code base to work natively on a number of different platforms. So that's the core message of PlayN. Write your code base once in Java, write your game once, and then compile out versions, native versions for HTML5, Flash, Android, and then you have the Java version as well. So that's what we're trying to do here. If you've been following Google game sorts of technologies, you might have heard of this before under the name of 4Play. So when this project was actually announced at Google I/O this year, so in May of 2011, this project was announced under the name of 4Play. It's just as same project essentially, but as it's gained momentum, as it's become more important to us and it's become really a part of our strategy, we've renamed it to PlayN and sort of formalized it. And there's all kinds of good developer documentation if you want to learn more about the project, the background, the APIs at developers.google.com/PlayN. So that's like your main point of reference. And so I know I said PlayN is an open source project, and open source projects can be kind of hit or miss. Like you might be wondering to yourself, a game is a really big technological endeavor. Is this something you can really invest your time in, build a really solid game on? And if you're wondering that, the answer is yes, PlayN is absolutely ready for prime time. If you want an example of some real game that has been done with PlayN, you should check out the HTML5 version of Angry Birds. So if you go to chrome.angrybirds.com or to the Chrome Web Store and you look for Angry Birds, you'll see the same Angry Birds that you sort of know and love probably running all in HTML5, and that was built with PlayN. So that's like, you can make a game of that performance, those high production values, all those you can do with PlayN. So that's sort of what it is. But why would you need this? Why is this an important problem? The problem that PlayN is trying to solve is actually the problem that all game developers I know of, and in fact all application developers are facing right now, which is just that we have too many opportunities, actually. We're suffering from a crisis of too many choices. The idea is we have all this great new technology. We have smartphones and smart TVs and new web technology and all this great stuff. Every time you turn around, there's a new opportunity to get your game in front of players. And that's awesome. That's really exciting. Until you start realizing just how much work it is to support that. So if you just try to do it the naive way, and you're like, okay, I have an Android game, that's great, I want to get this in front of more players, now I'm going to port it to JavaScript HTML5. Now I'm going to port it to Objective-C for iOS, and so on and so forth. This immediately becomes a development nightmare. It's a huge amount of time, it's a huge maintenance headache, it's just something that nobody wants to deal with. And that's where something like PlayN comes in, this idea that you write your source code once, and magically you get to work on a whole bunch of different platforms. It's a very natural thing to want. And if you're interested in web technologies, and here we are at an HTML5 conference, a very reasonable question to ask yourself is, well, isn't that what HTML5 is supposed to do in the first place? Isn't that what we've been saying HTML5 is for? that we have all these new devices. Every device has a browser. You write your game once in JavaScript, and ta-da, you're on every device that has a browser that renders JavaScript. And that's true a little. I don't want to, like, there are lots of good reasons to want to have your game in HTML5. And cross-platform is one thing you can target, one thing you can use HTML5 for. But using HTML5 as your primary cross-platform solution for games is difficult. And it's difficult because, not because of HTML5, because of the game part of that equation. The history of game development is the history of wanting more from platforms. Games are always the things that push the platforms the hardest and use the shiny new features and demand the most performance. And so, though it's true that an HTML5 game will sort of naturally render on a whole bunch of different browsers on a whole bunch of different devices, it isn't really fair to say that that will always be the most performant way to render things. And that's sort of a problem, because if you want to be the shiny new hot game on Android, you're competing against games that are using native APIs that have native performance. So if you want to keep up, you kind of need native performance. Again, it depends a lot on what you're doing. But for a lot of things, and this is sort of the proposition behind PlayN, if you need native performance, you need something like PlayN, and that's what it's for. All right, so we like this idea. We like the idea from a development standpoint of having one source code base that compiles to a whole bunch of different platforms. But we could have chosen any language. So why would we choose Java of all languages? And there are a couple of really good reasons. One is because we have the Google Web Toolkit, which I'll talk about in a second. And the other is because Java is just a really nice language that has a lot of stuff written in it already. And PlayN actually makes it really, really easy to just take that stuff wholesale and without doing much work at all, get that running in your game. So a great example of this is that there's this awesome physics library called Box2D. It's used in a lot of modern games. A lot of people already know it and love it. And it's just like, it's had a great success. And then there's a Java port of Box2D called JBox2D. JBox2D is about 11,000 lines of code. It's a big code base because physics engines are complicated things. We on the PlayN team wanted physics in our games, and we said, okay, what's out there? We don't want to write a new physics engine. Saw JBox2D, and we're able to take that and consume it, put it into our source code, have it working on all the PlayN platforms in about 30 minutes. About 30 minutes to port like a really complicated 11,000 lines of code. And that's really the power of what you can do with PlayN and what you can do with Java as your source language. And then the other really cool sort of thing about Java is that we have the Google Web Toolkit. So the Google Web Toolkit is the technology that sort of underlies all of PlayN. And what it is that before we were even concerned about getting onto multiple devices, web programmers already had this problem of having multiple source code bases. The idea that maybe you needed one version of your JavaScript that was optimized for IE, maybe you needed to do a different thing entirely in Chrome and Firefox and something like that. And even just at that level, that amount of complexity and having to maintain multiple code bases is already not fun. And that's the sort of first problem that I found that the Google Web Toolkit solved for me, the idea that you could write your source code once in Java, and then it would compile out different JavaScript versions that were optimized to different browsers. So if I needed to do something different for each browser, I could just be blissfully unaware of that as a programmer. And you open the JavaScript in IE, you get the IE version, everything's great. So you can see why this is a really natural foundation for something like PlayN. We were already generating different JavaScript versions. Now we just add into the mix different language targets. So now we just add in an ActionScript target and a Java Android target, and so on and so forth. And you can see this is a really solid basis. And so this problem of wanting to deal with the fact that there are many platforms out there is very timely. Like most game studios I talk to are either interested in PlayN or something like it, or they're developing this functionality into their own engine. I know very few people who are like, I'm on one platform and I'm happy. That's all I ever want. And you can also find all this middleware, which will help you sort of take you from any sort of source language to any target that you're looking for, depending on what your particular priorities are. But the thing that gives PlayN a leg up on all those solutions is that it's built on this really, really solid foundation. The Google Web Toolkit has been around for a long time. People already know it. People already use it. It's really stable. So it's just a great, solid basis for the technology. And then the other thing I wanted to point out is that a very important part of PlayN is this cross-platform notion. But even if all you ever cared about was HTML5, like you just wanted good HTML5 games, there would still be a lot of complexity there. So if you've tried to make an HTML5 game, you'll immediately run into like the headaches of different performance of different types of the HTML5 or different subparts of the HTML5 specification on different browsers. So for instance, if you wanted to make a sprite-based game in Chrome, probably the most performant way to do things is probably WebGL. If you wanted to be in Safari or Safari Mobile, you probably want to use CSS3 transforms, which is just a different type of HTML5. But this doesn't help you as a developer. You still need to write one source code base that's optimal over here and one source code base that's optimal over there, even though it's all within the HTML5 umbrella. And so PlayN can just sort of magically make that all go away. You just have the one Java source code base, and even within HTML5, it'll do the right kind of HTML5 for the right browser. And what that means is sort of what I just mentioned, the idea that your Chrome version will use WebGL, your Safari and Safari Mobile versions will use CSS3, all without you having to do anything. Audio is also a notorious sticking point for HTML5 games. There are these sort of intermediate libraries that some other people have talked about, like Sound Manager 2. They'll do something like trying HTML5 audio and falling back to Flash. There's usually that kind of complexity there. PlayN will just sort of mask that for you as well. It will attempt to use Web Audio API in your HTML5. If it can't do that, it'll fall back until it finds something that works. Again, you don't have to do any of that, which is really cool. So that's the sort of background information on what PlayN is. It's a way to get your code to multiple platforms without you having to be aware of the complexities of those platforms. Now, how does that all work? So the core structure of PlayN is this service provider interface pattern. And that's just sort of what that means is pretty simple. You have a core set of APIs and interfaces, and then implementations for each platform. So this is nice as a programmer if you're wondering to yourself, I wonder how this is implemented in Flash. I wonder how this is implemented on Android. It's all open source again, so you can just go to the implementation for that platform and poke around if that's what you're interested in. But it's all right there for you. And essentially, it's just platform-specific implementations. The concept behind the API from an engineering standpoint is that the core of PlayN, the thing we call PlayN, is really just the stuff that needs to be different on different platforms. So this is an important distinction to me because sometimes people ask me or say to me, Lilli, is PlayN Google's game engine? And the answer is no. That's actually a very incorrect way to phrase it. It's not a game engine. Game engines make a lot of choices about your game specifically. An isometric game engine is going to be very different than a word game engine and so on and so forth. PlayN is not about the gameplay so much. PlayN is about getting the same code to multiple platforms. And the amount of sort of game hooks we have in there is just the amount we need to be able to do that transition correctly. So we have the core API of PlayN, which is really cross-platform stuff like handling input, handling asset management, stuff that you really couldn't just sort of hack in unless you had platform-specific hooks. And then on top of that, we have modules contributed by the community or contributed by Google that there's this intermediate layer of supporting libraries, which is things that aren't really different on different platforms. They don't hook into a different part of the platform, but they're very general. Like UI libraries, we have some really nice third-party UI libraries out there. And then we have game engines built on top of that. So it's important as you go forward looking at PlayN to keep in mind the sort of structure. PlayN itself won't make gameplay decisions for you. All right, so when I say that the core of PlayN is really just the things that need to be cross-compiled, that breaks down into these three categories loosely. There's the game loop, which is sort of the only part of PlayN that's really specific to it being a game. And that's the timers that actually run your draw loop and your update loop and all that. And we have the I/O layer, and here we're defining I/O as input from the user, so like input managing from touch events and all that kind of stuff. And then output as output to the screen, so like your rendering system is part of what we're defining here as the I/O system. And then we have asset management. And asset management is loading resources from the local system, serializing them out to the server, or storing them in local storage, that kind of stuff, so all the asset handling. So those are sort of the three major breakdowns of what PlayN is. And I'll talk about them each. So first of all, we have the game loop. The game loop is essentially the way you make a game in PlayN. Your root level thing is an implementation of this game interface. And the game interface is really simple, and it should look quite familiar to anybody who's ever sort of written a game. You have an init function, which just sort of bootstraps everything, loads your resources. You have an update function, which runs your game logic every frame, and you have a paint function. And so when you want to make a PlayN application, a PlayN game, you just make an implementation of this interface. You fill out these methods, you hand it off to the system, and it deals with running it on the local system for you. From there on, it's not your problem. So the next part we have, so that's the game system, is actually like very simple. Then we have the rendering system. So say you wanted to get PlayN. You went and got the API tonight. You wanted to make a Hello World application. First thing you want to do, render a Hello World image. Probably your very first Hello World application, you code it up in Java, you look at it in HTML5, you put it on your phone, and it's probably going to look a little weird. And that's because each of those different screens has different screen characteristics. And as soon as you start getting into this cross-device, cross-platform programming, screen characteristics become a big sort of sticking point, what you do with them. So it's actually not that big of a deal to deal with, but you just have to be aware of it. PlayN provides you sort of a way to ask the local device for its current resolution. So you have graphics screen width and screen height. You can always ask, what's the resolution of the device I am on now? And if you're on a tablet or phone or something where that makes sense, you'll get the resolution of the device. If you're on Flash or HTML5 or something where that's not as clear of what that means, you'll get a default for that platform. And then this is another sort of place where it's important to us. We made an engineering decision around the fact that we are not a game engine. We're not going to decide what you do with this information. On the engineering team, we had these debates like, should we automatically sort of letterbox you or center you or do something that tries to help you be correct on the device? And we opted not, because actually people have very different strategies for how they deal with their sort of cross-device screenness. And they're very game-specific choices. So for instance, in tile-based games, when you render on sort of a more horizontal device like a phone, something with a very horizontal aspect ratio, often people just render more tiles out in front, so you can actually see farther if you're on a more horizontal screen. That's one way to do it. You could also center it. You could also letterbox it or whatever. And regardless of what you choose to do, none of that's very difficult. The code on this slide here, this sort of 3 or 4 lines of code, is doing letterboxing. So whatever you choose is not that bad. So that's sort of getting your device, your image, the thing you're rendering, oriented correctly. Next thing you're going to want to do is sort of understand how to draw stuff correctly. And that is through the layer system. So all rendering, anything that gets on the screen in PlayN is rendered through the layer system. There are a bunch of different layer types. And those layers have different performance characteristics, and they map to different output implementations. And I'll talk about them each in turn. So the different layer types we have, so we have a layer-based class, and then we have group layers, image layers, surface layers, and canvas layers. Group layers are just sort of group nodes. Then the layers that actually do rendering, like image layer, surface layer, and canvas layer, all come with a corresponding object that actually hooks into the rendering itself. So image layer comes with an image that does the rendering. Surface layer comes with a surface that does the rendering, and so on and so forth. Surface layer is probably the easiest layer type to understand if you've ever made, for instance, an HTML5 canvas game. It's a very sort of graspable, reasonable, traditional API. The idea is that you get very few functions. You have clear and draw image. But if you're doing a traditional sprite-based game, that's kind of what you want. And so the idea, if you were using surface layer to render your game, at the top of every frame, you'd clear everything, you'd draw your background tiles, you'd draw all your foreground stuff, and away you'd go. So very simple, pretty good performance. You can optimize beyond surface layer, but it's a great place to start. So I usually suggest that for your very first PlayN application, just do everything in a surface layer and then just optimize out from there when it's time to optimize. Group layers are, again, they're exactly what they sound like. They're an aggregator node. So the group layer is your hook into being able to make a tree of nodes. And the one layer that's owned by the PlayN system is the root layer. The root layer itself is a group node, and all your layers will be children of it. Group layers have nice functionality. Actually, every layer, including group layer, has methods that allow you to transform it around, that will transform all its children, to set its visibility and that kind of stuff. So it's really nice when you start needing to do complicated, sort of optimized kinds of things. I would recommend, again, don't start your first game by making sort of a deep hierarchy of layers. It's something you should do when it's time to optimize, but it's really nice to have it there when it does come around to that. And then we have image layers. So image layers are a really interesting one, really high performance, but a little bit weird if you're used to a more traditional rendering pattern. So the idea with an image layer is that it's a fire and forget image. You take an image, you put it in the layer hierarchy essentially, and then you don't draw it anymore. So there's a paint function, but you don't actually have to paint in the paint function. It's just going to get painted by virtue of being in the layer tree, which, your first time you're doing that sort of feels a little weird. The nice thing about image layers is that they're really, really high performance if you can sort of fit them in a way that doesn't confuse you. So if you sort of think about how this might map to sort of the HTML5 world, it's like, oh, this one output of the image layer could be CSS3 transforms. You can see you're just sort of moving things around on the page. They're kind of always there. So that's like a way to think about how image layers work. One really, really nice application of image layers is if you just want to do something totally static. So for instance, if you wanted to stamp your company logo and website over the top of your game, and you just wanted to stick it there, you didn't want it in your scene graph, you didn't want to think about it, it would always get rendered. That's a great application of image layer. Or similarly, if you have background art that's always going to be static, it's not going to confuse you to not be sort of painting at every frame, that's another great application of image layer. And then finally, we have Canvas layer. So Canvas layer API is by far the richest. It's actually a superset of all the other APIs and everything, other drawing APIs, rather. Canvas layer sort of is also the slowest. So it maps to the sort of obvious output implementation. So for instance, on Android, if you're rendering using a Canvas layer, the output rendering is going to use Android Canvas. In HTML5, the output rendering is going to use HTML5 Canvas. HTML5 Canvas is, of course, slower than WebGL, but you can do more stuff with it through this API. So the reason you would want to use a Canvas layer is if you wanted to do something procedural. That's pretty much the baseline use case for Canvas layer. And that's if you want to draw text, or draw rectangles, or draw circles, or lines, or any of these sort of APIs that are exposed by the HTML5 Canvas API. Those are great uses of Canvas layer. Again, it's kind of slow, but one thing you can do to optimize that is any layer can actually be any size. So just if you need to use a Canvas layer, make sure you're using a Canvas layer which is only as big as it absolutely needs to be. Transform it into place, and then don't update it every frame if you can help it. That'll help you get the most out of your performance, and you'll still get the nice procedural drawing that Canvas layer gives you. So this is just sort of an example, visual example of what a good layering strategy looks like. So I would suggest that for your first application, if you wanted to draw all these tiles in your game, you would just draw them all into one surface layer. Everything outlined in a red box is an individual image. Draw them all in there. When it's time to optimize, you do something like this. You take everything which is no longer outlined in red. You'd either put that all on a background surface layer that you don't update depending on your situation, or you would put them into image layers, something like that. Put it into the background somehow, something that doesn't get updated every frame. Everything currently outlined in red, you would put on a foreground surface layer that gets updated each frame. Something like that is a really good basic strategy. So that's pretty much rendering. So now that you can draw something, now we want to take input from the user. So input is one of those very platform-specific things, and as you can imagine. So the way PlayN sort of allows you access to what the user is doing is with a couple of basic abstractions. The most general one is pointer, and pointer is really nice because it receives whatever event makes sense. So for instance, pointer will take touch events if you're on a touch device. It'll give you click events if you're holding a mouse. So that's the really nice thing about pointer. It is, as you would expect though, a very minimal API. The only things you can get out of pointer are sort of pointer down, pointer moved, pointer up. But if that's enough for what you're trying to do, it's a really good choice. If you want to interact with the specifics of the input device, for instance, if you want to talk about left and right mouse buttons and mouse wheel and that kind of stuff, you'll want to use the mouse abstraction. Similarly, if you're on a touch device and you really want to talk about touch events, pressure, size, all the cool stuff you can get from touch events, there's a touch interface for that. And the way this works is that you ask the system whether these things are available. If they're not, it'll return null or throw an exception. I'll talk more about that in a second. So the way you hook into these things, set up listeners for these things from a programming perspective, is that there are adapter classes that come with each abstraction. So for instance, if you want to listen for pointer events, you make a pointer adapter, you set it as a listener. That pointer adapter will give you a method you can just fill out that says, on whatever pointer event. Fill that out and you're good to go. You're listening for pointer events. Similarly with keyboard, mouse, touch, they all work identically, essentially. You have an adapter class. It'll just tell you what methods you need to fill out. So oftentimes, it's nice to have things on different devices, but for extra good user experience, sometimes you want to hook into the input mechanism that makes the most sense on that platform. So for instance, if you're sitting in front of a multi-touch device, it makes a lot of sense to want to zoom by sort of doing this pinching motion. But if you've got a mouse in your hand, sometimes users expect that they can zoom by using the mouse wheel. So if you want to do something like that, where you really make a nice user experience and you adapt it to the platform that your player is currently on, you can do that. You can do that by asking PlayN for the current platform type and then making decisions accordingly. So that's what this slide is doing. It's saying, if the platform type is Android, I'm going to do some sort of touch-based zoom. If the platform type, and could go on from there and handle mouse specifically and pointer if it falls back and that sort of thing. And that's pretty much all there is to user input. That's sort of the general pattern for user input. The next thing that you probably want to do is fetch resources so that you can draw them or sounds so that you can play them. And the way you do that in PlayN is that there's a basic resource management class, this asset manager. An asset manager API, like many of the APIs in PlayN, is pretty terse. It's sort of exactly what it needs to be and nothing more. That's sort of our engineering philosophy. So we have these three methods: get image, get sound, and get text, and they'll do pretty much exactly what they sound like they do. They just fetch resources by that type. So this is an example of code for loading an image. The idea is you say, you want an image, you say, hey, asset manager, get me an image by this resource ID. It'll return you an image object. One thing to remember is that you'll be on one of many platforms. Those platforms actually have different characteristics for how they load resources and when those resources are available. So for instance, in the Java version of things, which is where people tend to do their testing, because it has very fast iteration time, you can just do everything in Java on your desktop. Resources like image resources, for instance, are available immediately. However, in pretty much every other platform, you need to wait until they're loaded, or you'll get a null pointer exception. So in this case, what we allow you to do, PlayN has this notion of a resource callback. Makes a lot of sense. You ask for the image object, then you add a callback that says, when this thing is fully loaded, I'm going to do something else. I'm going to draw this image in this case. But so that's resource callbacks for individual assets. However, if you're loading a level or doing something where you want to batch process a whole bunch of data, you need a slightly different interface, and that's where we have the Asset Watcher class. So Asset Watcher functions pretty much like a resource callback, except for it can do it in bulk. So the idea is you make an Asset Watcher, you have this done callback, which says, when you've loaded everything, do this. And then you can add resources to that, any kind of resource you want, or any kind of resource we support. So that's images and sounds and text. Then you can start that watching process. Once everything's loaded, it'll call the done function, which is how you would load your data at the beginning of your game, for instance. Sounds in PlayN are nice. As I mentioned before, they use the Web Audio API in the HTML5 version when it's available and sort of go through a series of fallbacks to find something that will work. It defaults to Flash at the end of the day. This is another example of where using GWT and Java really helped us out. So there's a lot of complexity trying to find the type of audio that will work. In our case, we were able to use this really cool library called GWT Voices, which already did this, already sort of stable and well tested and understood how to do HTML5 audio in a way that would really make it work everywhere, or get fallbacks such that you didn't have to worry about it. So we were able to just sort of pull that in wholesale. Other than that, asset management for sounds is just like asset management for images. You have resource callbacks, you ask the asset manager for a sound object, and away it goes. All right, so that's sort of fetching data in the form of assets. Now we want to save data. And there are two major types of saving data you might want to do in your game. There's local storage for just hanging on to things locally, like the user's current state or their name in the text field or that kind of stuff. Or there's heavyweight saving, which is like serializing your data off to the server. And PlayN provides utilities for both of those cases. So in the case of storage, local storage, PlayN provides this storage abstraction. Again, like a fairly targeted API, or quite targeted API. We just have set item, remove item, get item. It's a very simple sort of hash map-like interface. So if you've used web storage in HTML5 offline APIs, it feels a lot like that, where it's all strings. It's a 5 megabyte limit, so it's fairly constrained, but it's super, super easy to use. It's just like set key value pairs. So it's really, really nice for simple kind of things. And then for sort of heavier weight stuff where you actually want to hook into, all these different platforms have different JSON implementations. So you can hook into those through PlayN, through sort of PlayN's JSON exposed layer. And in order to get to that, you just say, hey, PlayN JSON object parse this resource object. It will then give you this JSON abstraction, which is sort of easy to read and write. Or easy to read. Writing is similar. If you want to make a JSON object, you ask the PlayN sort of core for a JSON writer. That writer has all the sorts of normal JSON writing functionality, where you can start objects and end objects and set keys and set values and that sort of thing. That's very natural sort of what you would want to do. So what I do in my local examples is when it fits, I just serialize that to JSON and store it in local storage, and if not, can serialize it off to the server. That's sort of a good way. It's a nice pattern to follow. All right, so what do we have so far? So we've talked about a main game loop, so your game has a heartbeat, it runs every frame. We've talked about how to fetch images and sounds from the system, how to render those images on the screen, and how to play those sounds. We've talked about handling user input and serializing sort of data, the local state, either to be saved in local storage or sending it off to the server. And that's pretty much the basics of having a game. Like with those basic components, you can do a whole lot of game. So imagine you have your game, you've used all these things, so you have a nice Java platform-agnostic version of your game in front of you, and now you want to take that and make platform-specific versions of it. You want to get that to new platforms. So how does that work? This is sort of the cross-platform magic. It's these tiny little entry point classes that bootstrap the system to fit on whatever sort of platform you're looking for. So for instance, if you want to make a Java version of your game, you make a Java class with a main function. You make a Java asset manager, which will tell the Java system how to find resources in that environment. You take your nice game class that you've made, this platform-agnostic game class, hand it to the PlayN system, and it'll just run. Similarly, like the HTML5 case, it's slightly different, but similarly simple. So in the HTML5 GWT sort of web world, the class that starts everything has to be a GWT entry point. So here we extend HTML game, which is a GWT entry point. We have this start method. Again, we have to tell the local system how to find the assets. So that's the HTML asset manager. And then we just sort of give our game to the system, and it runs it for us. Android and Flash are very similar, too. So the idea here is you just sort of register with the platform, and it will run your game. And so really, it's that simple. You make your platform-agnostic code, and then you just make these little entry point classes that do the very platform-specific stuff, which is mostly about finding assets or sort of bootstrapping. And the rest of your game lives in this nice sort of central code base. So that's sort of the basics of what PlayN is about, where we are now, rather. So what's next? We have a lot of things we want to do. We have a lot of plans and enthusiasm. So the number one thing I think that has been on our mind is supporting new platforms. And so that's like, for instance, one of the first things everybody asks me is, iOS, are you doing iOS? Will you ever do iOS? That's something we've been prototyping. That's something we're really, really interested in. And we really want to help our developers out. So whether the next thing is that or some other crazy platform, the really nice thing about PlayN is that, once you have things in this form, where you have a central abstraction and you have a framework that allows you to write new modules into the compiler, the sky's the limit, really. Like, you can always add more stuff. And we know we really want to do that. Then we have wanting native input abstraction. And that's a really close one to my heart, because I think that would help us have really good user experiences. And the idea there is that you can just make a Java image-based UI library that's, here's my button, it's an image, and it has this behavior. That's awesome. But each of these platforms actually has a native input library. So there's a text input on Android, there's a text input on iOS, there's a text input in the browser. There's native versions of these things. And I would like to sort of hook into the cross-platform functionality a way to tap into the native UI. And I think that would sort of make these things feel really rooted on their target devices. Then better asset management is very much on our minds too. Right now we have this 5 meg limit, we have strings for local storage. Those are like fairly significant constraints, and I'd really like to open that up to storing binary data and storing more data and using the file system API and so on and so forth. That's a big one for game developers, especially as we get people with heavier and heavier asset data. And then audio, of course, is another big one. So audio, of course, we already use the Web Audio API, but we don't actually expose we expose a tiny little fraction of its functionality. So right now you can sort of play, stop, set volume on sounds. Web Audio API is actually very, very interesting, very, very rich. You can synthesize sounds and analyze sounds and do all this really cool stuff. So I'd really like to be able to surface some of that more. The other really, really, really important thing for audio is that in games, you pretty much there are pretty much two types of audio in games. There's percussive ephemeral audio, essentially like gunshots and footsteps and that kind of things. And then there's long-lived sort of background audio, like music that you want to play and pause and that kind of thing. And in sort of rich, well-developed APIs, often you have separate abstractions for those two things, and you manage them differently. For instance, Android has buffered audio versus streaming audio. So I would like to, we don't surface that in PlayN, and I'd really like to. And I think, in fact, I'm fairly certain that would get us a lot more audio performance soon. So that's another thing on our major targets. And then the last one, another very important one, is integration with other products. And what I mean by that is Google has all these really cool technologies that are useful to game developers, all these kinds of APIs, and PlayN is an excellent place to sort of pull those together and make them available to developers in a really consumable way. And so one big success story we've had so far for integration is that we have several different types of payment API depending on what platform you're on. So for instance, if you're on Android, there's an Android in-app payments API, Android payments. And then if you're on Chrome, there's this other thing, which is the sort of web in-app payments API. They're both called in-app payments, which makes it a little confusing. But you want to use the one that's appropriate to your platform. And that's kind of a pain for developers because we went through all these contortions to try to get a nice platform agnostic source code base, and now we have something that needs to be different in each place. And so what we've done in PlayN is we've actually pulled in payments as part of the core abstraction. So now in PlayN, there's an in-app payments abstraction which will just route you to the correct API on the correct platform. And that's super, super nice. And to me, that's sort of really indicative of what we can do with PlayN. Because today it was in-app payments. Tomorrow it's going to be the next thing that we want to integrate with that needs to be different over here and over there. And it's a really great point to do that kind of integration. It's really useful, and it makes me feel sort of safe as a developer to know that when the next thing comes up, we'll be ready to sort of handle it in a very sane and sensible and easy way. And then, the other things, we're working a lot with sort of the community. There are a lot of good people out there doing awesome development. It's an open source project. Many of the developers are actually not Googlers at all. And so I'm always really excited when I see sort of third-party libraries come up. And so that's the other thing sort of I want to encourage is people to contribute to that community and make sure you look outside of just the core API, because there's a lot of really cool PlayN functionality out there, which isn't actually part of the core. All right, so in summary, if you learned one thing about PlayN, it would be that it's an open source project, and what it allows you to do is take your one Java source code base and compile it out into 4 platforms right now: HTML5, Android, Java, and Flash. And so that's the sort of core thing behind PlayN. And if you want to learn more, check out developers.google.com/PlayN, because that's our main documentation site, or definitely talk to me on Google+, talk to me on Twitter, talk to me at the conference. I love to talk about this. I will talk your ear off. And questions?
Not to be a Debbie Downer, but so what happens when it doesn't quite work right on a particular platform? Is there a way to specialize to improve features or performance on a particular platform?
Yes, that's a great question. It's a great and very reasonable question. Right, so 2 sorts of answers. One is that it's open source, so if it's not working for you, for your use case, it's actually a great escape hatch for a developer. You're like, okay, I need this functionality, I'll just add it my way, or I'll just fix this. Of course, you don't want to do that, but that's available for you. The other thing is when there's something you really want out of PlayN which isn't provided by the core APIs, one thing that people can do is compile out a PlayN project and then make a new project that's dependent on that. So for instance, on Android, if you wanted to do something really Android specific, and you couldn't get to it through the compilation path, you could make a PlayN project of sort of shared code, and then you can make an Android project that does Android stuff, import the shared code, and go from there. So those are the sort of 2 mechanisms for kind of getting around the constraints of the system.
So Java's, what's compelling about it in some ways is Java is a much more rich and performant language than either ActionScript or JavaScript. So what is your compilation strategy there? Are you using bytecode? Are you doing source code translation? How does it make that happen?
Compiling, you're asking about compilation from Java to...
Well, like if you're writing in Flash, right, are you translating to ActionScript bytecode? And then what do you do in HTML5, which doesn't have a bytecode representation? How does that pan out?
Right. So it's different for each platform. It's not bytecode. It translates to ActionScript, like legible ActionScript, okay. Yes, and then it compiles a Swift. At the end of the day, what you end up with is both ActionScript and a Swift, which you take and do whatever you want with. JavaScript, you end up with perfectly reasonable obfuscated JavaScript, gotcha. So you wouldn't be able to read it, but.
Gotcha. Interesting.
What's your minimum spec for Android version? And what hardware assumptions do you make on phones? I mean, so if your phone doesn't have a GPU, how do you handle that?
That's an excellent question. We don't have formal minimum device standards or specifications. We compile, and the short answer is I'm not 100% sure. I know right now when we compile to Android, our default path is to compile to Android OpenGL because that's the fastest way we can do things. Before we did that, we were compiling to Android Canvas always, which is not as fast. So I think if you couldn't do one, you'd get the other, I believe, but I'm not 100% sure. All right, I think I'm done with questions. All right, thank you very much.